Okay, let us begin once more. So, as I had mentioned before the break, that we are going to understand what is the meaning of this formula that we have just found out. So, let us take a look at this particular picture again. So, now what I'll do is I'll just draw the x and y. And what we have drawn separately is this cutting plane. On this cutting plane, I had the n hat like this. Now, try to think of it from a slightly different perspective. This is my x and y, and I have drawn an oblique cutting plane on which I have considered the unit outward normal. But is it not perhaps possible to think of it in a slightly different fashion like this, that I have my xy and I rotate my xy axis in such a fashion that my x coincides now with the n? I repeat, can I not think of it like this, that this xy, I hold it and I just rotate it. And I rotate it in such a fashion, in the anti-clockwise fashion, that it rotates by this theta such that this x now aligns with the n hat. Of course, my x and y remains the same. What I'll say is that that rotated coordinate frame, that will be the x dash y dash coordinate axis. So maybe with a separate color. Okay, so this angle, this is the theta. Okay, so instead of just thinking arbitrarily in terms of that cutting plane, I can think of it that I have rotated, or what would be my stresses if I rotate my coordinate axis by an angle theta. So it is in this perspective that Beer and Johnson has derived their formula. Okay, so what they say is that they have not mentioned any T and N. Rather, what they have mentioned is, what is this T and N now? You tell me in terms of the x dash and y dash. It is the sigma what? Sigma x dash x dash. Okay, so in the language of Beer and Johnson, this thing which we have just found out, that is nothing but the sigma x dash x dash. Okay, or this thing is the sigma x dash x dash. So this is the first of the stress transformation formulas. This is the first of the stress transformation formulas. Now what we want to do equivalently is that we have found out the sigma x dash x dash. Now we want to find out what is the expression in this transformed coordinate system of the tau x dash y dash. Okay, the shear stress. Okay, but we are not going to follow Beer and Johnson. We are going to stick with our system only. So earlier, when we talked about this arbitrary plane with the Tn on it, we could have also chosen to talk about the Tns. Now Tns will be lying along what? Exactly, it will be lying along the y dash. Okay, so Tns, it's itself nothing but the tau x dash y dash. Okay, all right. So next, we wish to consider the Tns, or equivalently tau x dash y dash. Now see, how did you obtain Tnn? Tnn was obtained using this formula, but this formula was derived from what? It was derived from the dot product of the traction vector with the unit outward normal, T dot n. So this thing actually comes from this T dot n. Okay, The normal component comes from the, if you take the component along the normal, so what will the shear component come out from? So if you take the dot product of the traction vector with the with one unit vector which is lying along the shearing direction. Okay, so what we'll do is this TNS equal to the tau x dash y dash, that will be nothing but the T vector dotted with the this thing. Okay, this is the unit vector along the shearing direction. This ES hat, what is it perpendicular to? It is perpendicular to the what? N hat. N hat. Okay, it is perpendicular to the N hat. Okay, now you tell me, you bring in all your knowledge of trigonometry and everything and vector, and tell me what is the expression of ES hat. Okay, you look at this picture, this is the N hat, this is the N hat. Okay, my ES hat is here. See, this is theta, this is 90 degree minus theta, this is also theta. So ES hat will be what? Yes, minus sine theta I hat plus cos theta j hat. Okay, very good. If all that is true, then this thing can be written as, in matrix form, as minus sine theta cos theta. Right? TNS is equal to tau x dash y dash can be written as T dotted with ES, which is nothing but T transpose ES. It is exactly like before. Instead of N hat, I am using ES hat. From T vector to this sigma transpose N, I am using the Cauchy's law, okay, which I have derived in the beginning of the class or the previous class. Now this becomes N transpose sigma ES. So slightly different from the previous case where we had N transpose sigma N. Now we have N transpose sigma ES. So now what we'll do is, my N still remains as cos theta sin theta. So this is cos theta sin theta. Because there is a transpose, I go from the column to the row form. Please do this multiplication quickly. Please do it. Please be careful with the signs because you now have some minus. Anyone? This is equal to minus sigma xx minus sigma xx cos theta sin theta. Okay? Plus tau xy cos square theta minus sin square theta plus sigma yy cos theta sin theta. Okay? So, this is okay. Now the form of these expressions are such that I know for a fact that you are itching to use, okay, go from this to twice theta. So we will relieve you of that itch. Okay, so we'll do it. So first of all, we'll take up this sigma x dash itself, okay, and we'll rewrite it. Sigma x dash. So please note this cos square theta can be written as what? So cos square theta minus sin square theta is cos 2 theta, and sin square theta will just replace it. So it is 2 cos square theta minus 1 is equal to cos 2 theta. I can never remember the formulas. I always mix up my minus and plus, so every time I have to derive it. So this is half of 1 plus cos 2 theta. Okay. Next, that is already God has given us the form. So this is tau xy sin 2 theta, and this sigma yy. So this is what? Half of 1 minus cos 2 theta. So we'll just make it look a little bit prettier. We'll take the cos 2 theta common. Right. And that thing, that has already come out in a very nice form. So we don't have to do much derivation. So this tau x dash y dash is nothing but, so this is tau xy cos 2 theta minus half sigma xx minus sigma yy cos 2 theta. Oh, sorry, sin 2 theta. Okay. All right. Stress transformation done. Right. But no. Okay, we are only, maybe 60% through it. So what we'll do right now is that we'll just look at it very lovingly, very affectionately. Okay. So this sigma x dash, you see, I mean, if you connect with your like inner JE mains aspirant self, okay, or maybe JE advanced self, some things will just come out to you. Okay, it will just surface to you. So try to connect the trigonometry with the coordinate geometry. Okay, so if I write it in a slightly different form, you will start to see something beautiful happening, and that is exactly what we are going to do now. Some of you who are very, very good in coordinate geometry can almost actually feel what is going to happen, even without me writing all these intermediate steps. But let's do the steps. So from this one, what we are going to write is sigma x dash minus, I will take this to the left hand side, sigma xx plus sigma yy by 2. That is equal to this sigma xx minus sigma yy by 2 cos 2 theta plus tau xy sine 2 theta. And tau x dash y dash, I don't have to do anything. Okay. What I'll do is, I will call this as equation 1, and I will call this as equation 2. Okay. So we square the two equations and we add them up. What happens? Well, so that is tau x dash y dash whole square, and over here this is sigma xx minus sigma yy by 2 whole square cos square 2 theta plus tau xy square sine square 2 theta, and I will get a term which is the twice AB term. But you please note here, this is also the twice AB term over here if I square it, but there is a minus sign. So when I add them, that plus twice AB will cancel with this minus twice AB. Okay, so effectively what I'll get is, I'm not going to write those extra terms, so I'll get from here please understand my feelings, okay? So this cancelled terms, I mean, this is the height of engineering laziness. Okay, proof that I was also an engineering student once. Okay, because I can see the terms cancelling, but cancelled terms. You might have heard of higher order terms, now you have seen cancelled terms. Okay, so please don't do this outside KGP. I just remembered we are recording all this. Okay. So what will happen? So see, ultimately what I'll get from all of these things is this very nice thing, that sigma x dash minus sigma xx plus sigma yy by 2, this entire thing square plus tau x dash y dash whole square is equal to what? You see, this is sine square 2 theta cos square 2 theta. So this is basically just sigma xx minus sigma yy by 2 whole square plus tau xy square. Because this is also sine square 2 theta plus cos square 2 theta. Okay? Now do you see something? What is that? Like if you just squint your eyes hard enough and pretend that sigma x dash is not sigma x dash, rather it is x. And tau x dash y dash is not tau x dash y dash, rather it is y. So it is x minus something whole square plus y square is equal to something square or something. Okay, so that is what? That is the equation of a circle, right? So where the center is where? Center is located where? Center is located at this sigma xx plus sigma y by 2. This is the x coordinate, comma 0. And the radius is root of this thing. Okay, root of the right hand side term. So how does it help us? Okay, I mean, looking at beauty is nice. Okay, it gives us a lot of peace. But beyond that, there must be some usefulness also. I mean, not always, but at least in mechanics of solids, there must be beauty and usefulness. So, if it is looking like the equation of a circle, let us draw the circle. Okay. What should be the x-axis? X-axis should be sigma x dash x dash. What should be the y-axis? Tau x dash y dash. Now in many books, it is not very clearly written that from that step to this step, suddenly they jump. And when they are labeling the axis, they don't make this thing clear that this is the x dash x dash. Okay, so when I was your age, these things used to confuse me very much. Okay, so it is what it is. Okay, so you're absolutely right to write it like this. Now, if I draw the circle and I tell myself that, let's say that sigma xx plus sigma yy by 2 is a positive entity. Okay, it need not be necessarily so. It is absolutely not necessary. But suppose I have to draw something, right? Okay, I cannot just, draw different options on the same diagram. So let's say that if sigma xx plus sigma yy by 2 is positive, then it should be shifted to the right. Okay, it will not lie on the origin. Okay, if sigma xx plus sigma yy by 2 is 0, then it is on the origin. So now the circle will look like this. Please accept that this is a circle, and please also accept that this is a diameter. Okay, this is passing through the diameter. Okay. Now, please note something very carefully. The radius is given by that. Okay, so we'll say that this thing is the radius. This is sigma xx minus sigma yy by 2 whole square plus tau xy square root of that. This is the radius. And this particular coordinate, that is what is usually referred to as the sigma average comma 0 point. Okay, where the sigma average is nothing but sigma xx plus sigma yy by 2. However, one important point to note, in every book of mechanics of materials, Hibbeler, Beer and Johnson, etc., you will find that this is written as sigma average. But this is sigma average with an asterisk. Because you see, suppose you go to the three-dimensional version, then what are the normal stress components? Sigma xx, sigma yy, and sigma zz. In that case, the average would be what? Sigma xx plus sigma yy plus sigma zz divided by 3. Let's write that. Okay. So sigma, let's call that sigma mean. So that is sigma xx plus sigma yy plus sigma zz. Now what did we do to go from the three-dimensional version to the two-dimensional version? Did we not tell ourselves that we are considering a special physical situation where the sigma zz is equal to tau yz is equal to tau xz is equal to 0? If that is so, then this sigma zz is 0. But this 3 doesn't disappear. Okay? This 3 doesn't disappear. So if in the plane stress condition you really want to write the true mean stress, then it should be actually sigma xx plus sigma yy by 3, not 2. So what is this thing? So this is the thing which will be useful for solving problems. So that is why I am saying this is sigma average with an asterisk. Okay, so this is Beer and Johnson average. Okay. See, cancel terms, new terminology, Beer and Johnson average, so many new things you are learning. Okay, probably in a more technical terminology, it will be better to identify this as the in-plane average. Okay, so within the xy plane, this is the average. But this is not the true average or the true mean stress. All right, now that we have some idea about this, can you tell me from this diagram, what is the maximum possible value of the normal stress? Sigma average plus R. And what is the minimum possible value? So sigma average plus R is here. Okay, so this is the maximum thing. So this is sigma average plus R. And this thing over here, this is sigma average minus R. Very nice. Okay. But suppose I ask you that from this diagram, it is very nice. We are noticing that sigma average plus R and sigma average minus R are giving me the extremum values of the normal stresses. But on which planes are they occurring? Because we have seen that you take an arbitrary plane on which the unit outward normal is like that. On which plane is that thing happening? How will you know that? So in order to investigate that particular question is not at all a trivial task. It may seem from this circle, it's very obvious, right? But in order to understand that entire thing is not so trivial or not so obvious. Okay, so that's a very, very important thing. So everything has been leading up to that. Why do I say this? Is that when you actually solve problems, nobody is going to just arbitrarily ask you, okay, you have got your BTech degree from IIT Kharagpur. Tell me at what is the value of the normal stress or the shear stress at an angle of 37.12 degree. Why would somebody ask you like that? Okay, only engineering professors will ask you stupid questions like that. Okay, just to test that you have remembered the formula or not. But in a real engineering field, the more important thing would be to ask you to find out what are the most dangerous situations in terms of the stresses. Right, because that is where failure can occur. And as an engineering graduate, your job will be to prevent all kinds of failure. Okay, so you want to investigate what are the maximum possible stresses that could occur, and even more importantly, where they would occur. Okay, so in order to understand that thing, we have to take up the next topic, which is called principal stresses. Okay, so by the way, this circle that you are seeing, it has a very special name. It is referred to as the Morse circle. This is the Morse circle. So this Moore, he was a German engineer. Okay, Otto Moore. So back in the, I think in the 19th century, he came up with this idea. He first saw this connection. Okay, between the stress transformation and this circle kind of form, and it is very useful to obtain the stress transformations in a graphical sense. But now, because we have so much access to computers, you don't need to know the graphical thing. Okay, it's actually not necessary. It is much easier to use these formulas. Okay, code it up and get the formulas. Okay, so nowadays, the Morse circle is actually used by engineers as a good visualization, as a quick visualization tool, but nothing more than that, not for actual calculations. But it's good to know this. All right, so we'll go on to the topic of principal stresses. Uh, where do I have this for? Acha, you guys tell me. Okay, I'm erasing everything. You guys tell me wherever something is appropriate. All right. Again, we are not going to follow Beer and Johnson. We are going to follow something completely different. So we'll take up this picture. This is our x-axis. This is the point in which we are interested in. This is the y-axis. And we have this arbitrary plane on which the outward normal is like this. Okay? Now, we have seen that in general, when you have this arbitrary cutting plane, the traction vector will have the two components Tnn and Tns. And we identify them equivalently as sigma x dash and tau x dash y dash. But now we ask ourselves the very important question. Can there be such a plane? Mark my words. Can there be such a plane on which the traction vector is lying along the unit outward normal itself? Okay, answer of course is yes, which is why this topic exists. Okay, so what we are asking is that the traction vector lying along the n hat. If this is the picture, tell me what is the value of Tns? 0. Okay, so in this situation, your T vector so the situation is like this. The T vector is oriented entirely along the unit outward normal. The Tns, the shearing component, is 0. In fact, this is the fundamental definition of principal stress, that on such a plane where the shearing stress is 0, that is what is referred to as the principal plane. In fact, it would be better if I write this as principal stresses and principal planes. Principal stresses and principal planes. Okay, so those planes on which the shearing stress are 0 or the shearing components of the traction are 0, they are referred to as the principal planes. Okay, and this Tnn, that itself is referred to as the principal stress. Okay, but now how do you find out that Tnn? Okay, so what we'll do is we'll again go back to the Cauchy's law. Okay, we'll again go back to the Cauchy's law. So we know that this T is equal to Tnn n. This TNN, because it is a very special thing, which is the principal stress, okay, principal stress, so we'll call this as the sigma p. P is for principal, okay. But what is this traction vector? This traction vector, is it not something like this? Sigma xx I'll write it a little bit carefully. First, the matrix representation. So T is sigma transpose n. This is equal to sigma p nx ny. Let me keep this as n only. Okay, now sigma xx, tau xy, sigma yy. The n decomposed into nx and ny, we have already seen that is nothing but nx equal to cos theta and ny is equal to sin theta. But see, we are not looking at some arbitrary cutting plane. We are not looking at some arbitrary unit outward normal to that arbitrary cutting plane. Rather, we are looking at a very, very special kind of plane on which the entire traction vector is oriented along the n. So this kind of a principal plane will be depicted by this theta p. It is just to remind ourselves that we are not looking at some arbitrary plane. Rather, we are looking at this very special kind of plane, which is the principal plane. Now, linear algebra back into action. Okay, the physics and the geometry we have taken care of, now linear algebra. So see, here this is a column, this is the same column here. I can transpose it to the left hand side. Okay, I can transpose this to the left hand side and I can write this as what has this started to look like? Yes, Ax equal to B, where B is 0, 0. But does it remind you of something, some special kind of problem? Sorry? Why? I mean, you have skipped in one go like 2-3 steps. Determinant equal to 0, yes, certainly. Determinant equal to 0 will arrive at that. But please tell me before that. It is like my son. Okay, he sometimes talks about his grandkids. He is 7 years old, by the way. Okay, so it is like that. I mean, there are a few intermediate steps left in between. So that problem, it looks like an eigenvalue problem. Okay, it looks like an eigenvalue problem. Now, what is the, I mean, in order to go towards determinant equal to 0, what is the argument? What is the logic? We want to have a non-trivial solution. Absolutely correct. Non-trivial solution of what? Yes. We want to have a non-trivial solution of this theta p. Okay, we want to have a non-trivial solution of this theta p. What is the meaning of that? A non-trivial solution of theta p. What is a trivial solution? Theta p. So what is a non-trivial solution? Physical meaning? Meaning is that we want to be able to find such a plane, we want to be able to find such a plane where all of these conditions would be valid. Okay, that is the logic. So in order to find non-trivial solutions of this theta p, what do we need to do? We need to use the condition that the determinant of this matrix is equal to 0. Okay, so for non-trivial solutions, let me keep this. What does this give me? So does this seem correct? Something is missing. Plus sigma p square. Okay, so here the unknown is what? Sigma p. We want to find out the roots of sigma p, right? Okay, so sigma p will be what? So this is in the quadratic form, the quadratic equation form. So this is the ax square plus your bx plus c. Okay, so I'm skipping a few steps here. So this is sigma xx plus sigma yy. So this is minus b plus minus b square. Minus 4ac. Minus 4, this is 1, a is 1, and c is this entire thing. Sigma xx, sigma yy, minus tau xy square. Divided by twice a. So twice a is just twice. So if we have all of these things, then so what I want to do is, I want to write this part separately, which is what I've already done. And I want to write this thing separately. I also want to take this 2 inside the square root. So what will happen is, plus also note that this is a plus b whole square minus 4ab. Okay, minus 4 sigma xx sigma yy. So overall this will be sigma xx minus sigma yy whole square. Okay, so this is sigma xx minus sigma yy whole square by 4, and that is minus 4 minus tau x square, that is plus 4 tau x square, divided by 4, that is tau xy square. Now, look at this radius that we had obtained earlier from the Mohr circle. Okay, so everyone look at this side of the diagram, this side of the board. Earlier, from the Mohr circle, we had obtained this radius. So, is it not in that same exact form? This is the same form that we had obtained earlier. Now, what is the advantage? Earlier, courtesy Otto Mohr, we had obtained with pure German efficiency such a nice thing. And after doing all that mumbo jumbo, we have arrived at that same thing. What is the advantage? Well, the advantage is that now, because you have arrived at through the proper mathematical form, you can go back and find out the expression of the theta p. Okay, so that is what we are going to do. So, so the equations that we had earlier were this: sigma xx cos theta plus tau xy sin theta, all of these are p's, that is equal to sigma p cos theta, p. Whatever the matrix equation I had, I am just extracting out the equations out of it. Okay, the linear simultaneous equations out of it. Tau xy cos theta p plus sigma yy sin theta p, that is equal to sigma p sin theta p. Let's call this, I don't know, what was the last equation we used? 2, I think, right? Let's call this 3. I don't know why I'm writing the hash. Anyway. Okay, so I want to find out, what I want to do is I want to eliminate my sigma p. Okay, I want to eliminate my sigma p and I want to find out theta p. But please note that this is only a mathematical hack. This is not the way to find out the eigenvectors. If you have a 3 by 3 matrix, this trick won't work, right? There is a proper method to find out eigenvectors. This is the lazy engineering way. Okay, answer will come. Okay, so what do I do? Well, algebraic manipulation as always. So we want to find out, what do we want to find out? We want to find out the theta p expression. Okay, this is not helping us. We want to find out such a situation, or we want to arrive at such a step where the theta p's will all be in the same side. So from here, what we'll do is, on this left hand side, we'll divide the numerator and the denominator by cos theta p. Okay. So what we'll get is tau xy plus sigma yy tan theta p divided by sigma xx plus tau xy tan theta p. This is equal to tan theta p. So I'm skipping 2 steps, okay? In my head, I'm doing this thing that I'm taking this denominator from the left hand side upstairs to the right hand side. So I'll get sigma xx tan theta p plus tau xy tan square theta p. That tau xy tan square theta p I'm bringing to the left hand side, and I'm getting 1 minus tan square theta p. On the right hand side, I have left this sigma xx tan theta p, but on my left hand side in the numerator, I had this sigma yy tan theta p. So I'll bring this side. I want my answer for tan theta p. Okay. All right. I want my answer for tan theta p. What do I do? Right? Right. So the only thing I'm missing here is a 2. So whatever is missing in life, I bring it in. Okay. As easy as that. All right. Now you tell me, uh, how many solutions in general are you going to get out of it for 2 theta p? So suppose I supply you with numerical values of this tau xy, sigma xx and sigma yy. The right hand side will come out as a certain value. Corresponding to that value, will I not get 2 values of this twice theta p? Okay. So I will get twice theta p1 and twice theta p1 plus 180 degrees. Right? Why? Why? Yes. So tan pi plus theta is equal to tan theta. Okay. Which means, please note that my 2 theta p is not the angle. It is actually the theta p. So this is theta p1 plus theta p1 plus 90 degrees. Okay. So whenever you are finding out, now this may look all very abstract, and I mean, where is the mechanics of solids in this? But when you actually start solving problems, you will see that you will actually get 2 planes which are perpendicular to each other, where you will get the principal stresses. Okay, so this is very, very important. You please mark this. Okay, so this is very important. Okay, I have run out of time. I wanted to I need to discuss some things more. So, well, we'll have to continue tomorrow. My plan was to start with strain tomorrow, but we'll have to continue with this tomorrow. Thank you very much. Stop.